Hi, Bobcats. In this section, we're going to take a brief look at chemistry as an entire field and also look at some of the big themes that are going to be found in this course. So specifically, we are going to describe the field of chemistry and how it fits in with other disciplines, and then look at these major themes. Each one of these recorded video lectures is going to have an objective slide at the beginning, and then most of the time I'll repeat this slide at the very end. These objectives are so important. When you are getting ready for an exam, you need to review these objectives as a checklist. If you can describe something about how chemistry is related to other fields, then you can put a check mark by that objective. And when you can put a check mark by every objective, you're in great shape for the exam. When I look at this diagram from our textbook, it really just cracks me up every time I see it. The thing about this is it makes chemistry look like it's absolutely the center of the universe. And while I would love to admit that that is true, reality is that science and all of these other fields have this complicated interrelatedness. So for instance, we can take principles of chemistry and apply them to agriculture and improve crop yields, or get rid of a pest that is eating crops. But chemistry alone can't improve agriculture. There's a lot of engineering that goes into that, as well as all of the biological sciences. So as much as I would like to say chemistry is the center of the universe, it's really part of a complex web of all of these disciplines. Chemistry, or at least modern chemistry, is often defined as the study of matter, energy, and how they interact with one another. So we can use chemistry to explain the bonding in sodium chloride, which is the crystal shown on the left image on the bottom. We can use chemistry to figure out, for instance, what elements are present in the sun. So if we know about how energy in the form of light interacts with atoms, which is a type of matter, then we can learn which atoms are present by looking at the light that reaches Earth from the sun. On this slide, we have the list of ingredients of something that you can find at a store. First ingredient doesn't sound too bad. It says aqua, which is just a fancy word for water, and then it has sugars in it. Then the next words are a little bit not so common: fructose, glucose, sucrose. When you see that OSE ending to a chemist, that just means that particular chemical belongs to the sugar family. Then there are a bunch of acids, some amino acids, glutamic acid, aspartic acid, leucine, arginine, alanine. Let's see, what else do we have? Skipping down there, we have some omega-3 fatty acids. We have some flavors that have some really funky sounding names, like butyraldehyde, pentanal. Yeah, some of those names sound a little bit scary. There's benzaldehyde down there towards the end. So it kind of makes you wonder, what in the world is this thing? Well, believe it or not, this list of ingredients is the chemist's view of something that naturally grows, blueberries. So if you look at all natural, organically grown blueberries, these are the chemicals that you find when you do a chemical analysis. The point I'd really like to make with this slide is that to a chemist, any type of matter is a chemical. It doesn't make sense to a chemist to say something is chemical free. If somebody is trying to sell me a container and tries to claim that everything inside of that container is chemical free, then I would expect that this person is selling me a container that is absolutely empty, because to a chemist, all matter is a chemical. When we look at chemistry through the ages, Modern chemistry really got its start or has its roots in something called alchemy, which was before about 1500. The goal of the alchemists was to try to turn some sort of a cheap metal into gold or some other cheap substance into gold. And along the way, the alchemists developed the foundations of our modern lab techniques that are in use today. Modern chemistry really started developing around 1700 or so, um, which is how we wound up at this definition that chemistry is the science of matter and energy and how they interact. The chemical company DuPont has a slogan of better living through chemistry. And modern chemistry has all sorts of wonderful products, things like fertilizers, pharmaceuticals, and even in my professional lifetime, I have seen a big push for green chemistry or sustainable chemistry. And there are pieces about green chemistry scattered throughout our textbook. Every chapter has a section on green chemistry. It's really a mindset. It's a commitment to try to consider a chemical's total impact. Maybe this chemical is absolutely great for this one reaction, but if it's absolutely horrible for fish and any disposal technique is going to cause some of this chemical to leach into a water supply, then we really don't want to use that chemical. So that's kind of the thought process behind green chemistry. And we are considering the impact of the chemical from the cradle to the grave, which means that we want to think about once the product involving this chemical has reached the end of its lifetime, what's going to happen to it next, and what sort of an impact will that chemical continue to have. One of the major themes we'll see in this course is the search for patterns. This particular table is a periodic table published by Mendeleev around 1870. Mendeleev was looking for patterns in chemical reactivity and trying to use those patterns as a way of organizing the known elements into some sort of a table where the actual arrangement of the table itself would hold extra information about the chemicals. So for instance, you could see where the element was positioned in the table and make a bunch of inferences about how that chemical would react. We're going to look at a number of models this semester as well. This particular slide is illustrating the atomic model. So atoms are the smallest particle of matter that chemists are usually concerned with. And the models are best when they help us with explanations or when they make predictions. For instance, some theoreticians had predicted that a molecule composed of 60 carbon atoms, known as C60 or Buckminster fullerene, would be a stable arrangement of those carbon atoms. And that made scientists go and try to find them. They finally caught them actually as a little blip that kept appearing in a particular type of apparatus where they were studying other things. And then they discovered, wow, we actually have these molecules of Buckminster fullerene. But they also predicted by looking at the energetics of the molecules that not only would this closed ball of 60 carbon atoms be stable, but these tubes, hollow tubes of carbon atoms known as nanotubes would also be stable. And so the value of our models is greatly enhanced when we can make predictions off of them of things that have not yet been observed. Chemical reactions are another big theme in this course. I still think about the coolest thing I ever do in lab is when I mix two chemicals together and there is a sudden significant change. In this particular case, potassium iodide and lead nitrate are being mixed. Alone, each one of those solutions looks just like water, but when you combine them, this bright yellow solid or precipitate is formed. And these chemical reactions that involve those sudden dramatic color changes or sudden production of a precipitate, those types of things are just about the coolest things that you can observe in lab. So in a face-to-face class at this point, I'd like to ask this clicker question. I'd like for you to decide, are chemicals good or are chemicals bad? Now you might want to pause the video for a moment and think about that. Okay, so hopefully you paused it, you came up with an answer. Now I'll share with you my answer. I'm going to call BS, which stands for bad science, on this question. This is an example of a false dichotomy. I'm asking you to pick between two choices and not giving you any other choices. And honestly, I don't think either one of these choices is a good choice. Instead, I would argue that chemicals are neither good nor bad. When you don't know what you're doing with chemicals, or you deliberately ignore the protocols that you're supposed to follow with a chemical, you can cause all kinds of problems for yourself and for other people. But when you use chemicals properly, you can do all kinds of wonderful things. You can save lives with things like drugs and vaccinations. You can improve the quality of life. One of the things that I find amazing is the value of fungicides. When my daughter was little, we would buy strawberries at the grocery store, and if we didn't use all of those strawberries within 3 or 4 days, guaranteed the remaining strawberries were going to be covered with mold. Today, that's not the case. We can keep strawberries for up to a week or sometimes even more than that, and the strawberries are still just fine. That's the power of a fungicide. So when chemicals are used properly, they can do all kinds of wonderful things, but if chemicals are used improperly, they can create all kinds of problems. So last but not least, we're circling back around to our objectives slide. And hopefully after going through this video, you can describe the field of chemistry and how it's connected to other fields, and also talk about some of the major themes for this course, like searching for patterns and using models.